Actually, I'll just make a quick note of that before I forget on water quality. Under BioEarth, but then also the project I'll talk about here, is a lot of the difficulty comes in with that issue of deficit irrigation. There's some really difficult interactions to model between as you reduce water application, what the optimal fertilizer rate is, which has an interesting, important effect on water quality. So that's part of what we're going to hope to do. I'm going to mention that now because I don't cover it in the presentation. So, okay, well, my name is Mike Brady. I'm an assistant professor in the School of Economic Sciences at WSU. I'm also going to make a quick apology I find myself making in front of this sort of audience, is that I'm one of those economists that suffers from having extremely boring slides relative to climate scientists, engineers, hydrologists. One of these days I'm going to get better at this, but all these really nice, colorful graphs and pictures, we tend to, not all economists, but many of us tend to not be so great at that part. So I apologize for the stark slides in advance, although I made that apology before to different groups. The name of our project is WISDM. This talk is on really I'm going to focus on sort of one aspect of the project. I'm not going to give a full overview of the project. Part of that is that reason for that is I've actually just stepped into the role as the PI on the project. A lot of credit goes to Kaylin Hakor for serving as PI for the first 2 years of the project. She's left WSU and then so left being PI as the project, and so I stepped in this summer. So part of it is time, part of it is I'm still probably learning all aspects of the project relative to what I knew before. So I don't want to shortchange all the other work that others are doing, but I'm going to be a little more focused here, but I did want to give a list of the co-PIs. So we've got folks from WSU, Idaho, Central Washington, and University of Utah on there. So, okay, so I don't expect you to read all this. This is our logic model for the project, but I just wanted to point out a few sort of key terms that I'm going to focus on. This hopefully gives some perspective of all of the modeling that is going on in the work, but I'm going to focus on the parts that I have here in red. So down here on the left, we have the issue of regulatory institutions, where we want to explore how water users and regulatory institutions adapt as water scarcity increases. So not only how a bottom-up adaptation occurs, but then also how the institutions that manage water change as water scarcity increases. Up here is collaborative modeling, which is a key part of WISDM, and I think it could be said probably the sort of the centerpiece that makes it stand out from other related projects we have. So I'll talk about that. And then also down here, improved modeling assumptions, which are really relate back to this both regulatory institutions and then the collaborative modeling. The objective for all of those is to improve our modeling assumptions for projects like BioEarth, large integrated projects, where for the most part, at least I guess from my perspective, what we're really taking is we're trying to model the effects of climate change to somewhat of a degree, taking sort of the larger institutional environment as fixed, I guess you could say. And we're going to allow individual, we call them agents in economics, allow them to respond, but there's not a lot of large-scale change and sort of from the top. WISDM's a little more focused on that. So this is sort of the larger project, but I'm going to focus specifically on those aspects of it. So the key motivation for WISDM was an interdisciplinary group had experience in model development integration in previous projects like BioEarth. But what WISDM had a little more of, well, like I mentioned before, that there is a significant model development component in WISDM. What we have a little more of, well, probably a good bit more of, is I guess you could call social science integration. So management, political action, economics, and law, which actually some ways prove to be more difficult. Because I think economists and engineers actually probably have a history of working together pretty easily. And it can be more challenging to integrate along the social science dimension. And that's a big part of WISDM. So what is the goal of at least this part of the project? Well, I'm going to talk about the part that I do a lot of, which is to do a big chunk of empirical analysis to better understand both bottom-up and top-down decision making. Well, what's the result of that? Well, hopefully we can improve the predictive ability of large integrated modeling efforts. You could view it as improving the parameterization of the models. But then also identify key decision-making characteristics that can simplify modeling. As we try to put more things in, they get increasingly complicated. Are there things we can learn about how decisions are actually made that can actually allow us to maybe simplify some of our model structure? I just want a quick note here on, since I think sort of economists are probably a minority in the room, the two difficult aspects to modeling human decision making that are always a challenge is that people are forward-looking, which is maybe a bit different when you're doing climate modeling without the sort of the human dimension. Even as I said there, even though it often looks as if people are not forward-looking, but we are in a university campus. People go to college because they're forward-looking, right? So. The difficulty here is that and a lot of these models exist, but so dynamic models with those expectations can get very complicated, right? So people anticipate changes and they act now to those changes. Incorporating those expectations can get very difficult and complicated, particularly as you try to do it in an integrated modeling framework. Maybe not so much when you're just trying to do an economic model, but it can get very difficult in an integrated framework. Also, another difficult part about expectations is that there's all the public information out there about drought probability, but how do different people form their expectations of what's the probability of a drought next year? How does that depend on their age, their finances, other demographic characteristics, what crops they grow, that they'd actually make different expectations about the chance of a probability of a drought. But then we're always, maybe we don't get it right for every person, but we want to get it as right in the aggregate as much as possible. And then also the fact that people have different preferences that shape priorities. One we hear a lot in, I think that it gets thrown out a lot in this realm, particularly with water trading, I've heard is that, well, this irrigated farmer, this water right holder, they won't sell water at any price, right? Which infers this preference for how water is used, and they're willing to say, even if someone is willing to offer them more money than what they would make by using the water themselves, that is their preference, that they will not sell the water. So we'd be a little suspicious of that as economists, but we want to try to actually capture that a little bit more. And also, where this gets a little more complicated is the interaction between the economic and political systems. And it used to be 100 years ago called political economy, which I think was a little more of an explicit accounting of the fact that the economic and political systems work closely together. Okay, so the first part I want to really talk about here is this trying to incorporate endogenous institutional change, probably somewhat of an economics jargony term. But what I mean by that is we want to avoid modeling changes in water management institutions in an ad hoc way. To give a specific example for this, we've worked on a project related to state climate change forecasts, and it happens every 5 years. And in the last iteration, when we get down to the end in scenario development, there's a lot of, there's some political back and forth about, well, what are all the scenarios we should model? Should we consider, well, what if water markets, develop? Okay, we could model that. Well, what if there's a water right adjudication in another basin where there hasn't been previously? How would that affect water use? It's like, okay, well, we could model that. What if there's water quality trading that develops? Okay, well, that'd be interesting. We could do that. The only problem, though, is that, of course, underneath it, there's always a political game being played there. So those what-ifs could be modeled, but I think a better way to do it well, without a greater ability to predictively model them happening in a probabilistic way, you can get into problems because there's a lot of political motivation to consider certain scenarios that may not happen or be very unlikely to happen. And I just want to mention Barb Cousins here specifically is a real expert in water law that can get at what is possible, and we can combine that with our economic analysis to really try to understand, well, let's not just throw random scenarios at the board. Let's try to understand what's likely to happen from an institutional change standpoint. Okay, so we want to quantify to actually model this, we want to be able to quantify the distribution of costs and benefits across stakeholders and model incentives present to seek to influence change. So what do I mean by that? We don't want to just consider these things just happen randomly. What's a specific case? Well, there was a basin-wide adjudication in the Yakima that began in the late 1970s. So rather than use that as motivation, say, well, let's model an adjudication happening in this basin. We want to step back and ask the question, well, why was there a basin-wide adjudication in the Yakima Basin? What was the cost? What changed? How were the costs of water scarcity borne across junior rights holders, senior rights holders, interruptible rights holders? What was the scenario that led to this legal action? And if we can answer that and try to learn something about that, maybe then we can also understand why an adjudication or predict when adjudication would happen someplace else, right? So that's the sort of questions we want to ask. What is it? Why does it matter? Well, adjudications fully define property rights, so that's a goal, over water, which is an important prerequisite for water trading, right? So again, what if water trading starts here? Well, do they have to have an adjudication first? How likely are they to have an adjudication? Oops. Quick another example, the Kittitas permit exempt well moratorium has been a fairly big deal. That's another case of where you've got incompletely defined property rights over water. But a moratorium went in 2009 to restrict permit exempt wells in the upper Kittitas. This gives us another case study to use, empirical analysis to understand, okay, what were the conditions such that this political action occurred? How were the costs distributed across different stakeholders in that basin? How did they influence political change? So how bad did it get before they acted? The answer to this helps us understand when incomplete property rights problems are addressed, something economists think a lot about. The problems you get when property rights over a resource are not fully defined. Well, when do they get fully defined? What are the conditions such that that happens? And then also we've got a component of the project going back into other states that have had more severe water scarcity problems than us to look at when their water markets developed so that we can actually use that to inform our modeling rather than doing something a little more ad hoc. A quick final example. With water rights, they're historically based on diversions rather than consumptive use. Ideally, they'd be based on consumptive use. Well, why was that? Well, transactions costs are most likely quite high, particularly 80 years ago, to monitor how much water was actually used. Will this change as information technologies develop, where monitoring consumptive use costs go way down? That's something we want to consider. Also, as water markets develop, usually trades are based on consumptive use, not on diversion quantities. So as water markets develop and water is transferred, you increasingly have a system of water law based on consumptive use rather than diversion of quantities, which affects return flows. And then each individual decision can affect the aggregate water scarcity. So those are the cases where we want to take events that have happened, analyze them empirically to try to do a better job of forming model scenarios. The second part I want to talk about is the participatory modeling. So Alison Beale King is really our leader here. She's in the School of the Environment at WSU. The approach she uses of participatory modeling has two main goals. The first is to provide a system for stakeholders to better understand the functioning of the hydrological system. So these are folks she's worked a lot in the Spokane, and now she's starting to do more in the Yakima, where you get various stakeholders who sit down at computers and start to interact with a representation of the hydrological system, and to learn about how it actually works. She's interested in that in a couple different ways, for a couple different reasons. One is does that influence their perspective on the problem or willingness to consider other solutions? And it also, we're hoping to sort of bring in more aspects from behavioral and experimental economics, which behavioral economics is particularly focused on things like cognitive biases, or how people focus on certain pieces of information relative to others, and how that influences their decisions. We want to try to use the participatory modeling framework to reveal important aspects of human comprehension, decision-making, and preferences, and how those interact with their understanding of really the science of how coupled human and natural systems work. The real holy grail as we try to develop these more complicated integrated modeling frameworks is, can we identify decision-making characteristics that allow for simplifying models and improved predictive ability? So we could develop some really rich, somewhat complex models previously, but as I mentioned, once you put them in an integrated framework, that becomes more and more costly. So when you can find cases where, for example, say a number of farmers use certain rules of thumb that actually allow you to simplify their expectation formation, but then also simplify your model relative to what you would do without that information, that can really help improve both the sort of the tractability of the model, the complexity of it, but also then the predictive ability. And here's just, this is Allison's schematic of sort of how our participatory modeling framework. There's a software system that tracks all of these interlinkages, and folks sit down at computer terminals and get to adjust things. They get to simulate policy changes, population growth, changes in climate, and they can make decisions and see how the system responds. And so I mentioned this a little bit before, but through that framework, we can understand what people focus on, which aspects do they attempt to change, how does that respond to the information they were just given. We can also look at whether stances on preferred policy responses change as understanding of the hydrological system improves. There's been a number of papers in Nature Climate Change and other journals about this question of understanding of science and positions on policy, and we're hoping to inform that. Okay, let's see, almost done. So I'm just going to mention a couple other empirical studies that use a specific technique we're finding that's out of the econometric or sort of statistical economics literature, which has proved really valuable in fields like labor economics. And we're also finding it useful in this context, which are often called quasi or natural experiments that help with statistical identification, where you have sort of a historical accident or a policy that went in that you then can identify the effect of that policy in a way that would be easier than if, say, you took all the schools and increased funding all at once, right? So it's sort of we call them natural experiments. It's like you could do a laboratory experiment, but it happened naturally. One example I'll give here is, well, I mentioned this before, but we know farmers are heterogeneous in a number of ways. They use rules of thumb, and also they form expectations of future conditions in different ways. The one aspect with deficit irrigation we understand, as an economist, we're a bit surprised that that's considered a departure from what people actually do. The only time we would expect that is if water's free, that you would actually irrigate to maximize physical yields. However, monitoring soil moisture and other things is costly. There's a time cost there. So we want to know, how do farmers actually adjust their irrigation scheduling? Are there signals that they actually respond to adjust things? And that's where we can start to look at actual observed irrigation scheduling and try to reveal those sorts of things. A good example that kind of falls into that kind of natural experiment case. In the Yakima Basin, there's two basins that are right next to each other. One is essentially never curtailed. The other is curtailed about once every 5 years, about 50%. They're really similar in almost every other way, the crops they grow, the soil types. So we want to use that as a test case that, what do we expect with climate change in this region? Well, at least initially, kind of subtle changes in the probability of drought. Well, we can use these two irrigation districts as a test case to consider, well, how much do farmers respond by investing in more efficient irrigation systems that limits their costs during droughts as droughts become more frequent? Well, we can use this sort of historical accident as a case. And what we find is that irrigators that are curtailed about 50%, one in every 5 years, are about 5% more likely to invest in an efficient irrigation system. Well, why does that matter? Well, the efficient irrigation system, while it's often promoted through state policy as a way to deal with climate change, as irrigation efficiency improves, return flows decrease, and has the unintended consequence of actually in a drought exacerbating the problem of the drought, as long as you have a system of water rights based on diversion quantities. Right, so it's actually, this is a really important part to understand of, we want to model an increasing frequency of drought. Well, to understand the aggregate scarcity problem, we'd want to allow our model to allow irrigators to put in a more efficient irrigation system if we think that's what they would do. This gives us information about how much more likely they would be to do that. Then we can use that to understand, well, how much do return flows go down in a severe drought because irrigation efficiency, well, more efficient irrigation systems are being put in at what rate? Right, so that's the way we're trying to couple increased use of empirical analysis to improve our modeling. Okay, so just to conclude here, a critical component of understanding feedbacks is institutional change. So the participatory modeling gives us a lot better understanding of how individual decisions are made, things like rules of thumb, what information is paid attention to, subjective expectation formation, all of that sort of stuff. But then we can also use our empirical analysis to understand, when did institutions change? When do water rights adjudications happen? When do water banks appear out of thin air, right? And this has an implication both for improving the predictive ability of our model, our capacity to develop integrated models, which the aspect of integration makes it very complex. How can we use these to simplify what we're doing to allow greater integration? But then also the important aspect of scenario development, so that we're not just sort of throwing out ad hoc scenarios. Okay, and that's it.
Roy Haggerty, OSU. This is a bit of a philosophical question, but I think to me it's an important one. When we model the future of physically based systems, the rules of that are based on differential equations and physics that are pretty well understood. Human institutions, of course, economics, there's that, but a fundamental component of any human decision is a piece that we do not have an understanding of at the moment, and that is how ideas come about. Human beings develop ideas, and clearly new ideas generate new ways of operating human systems. Yeah. So we don't understand one of the physical fundamental laws that underpin the future. So how do you go about modeling that?
Well, so I guess I would say there is a history of that in economic analysis. There's Vernon Rutan, it was at Minnesota for years, there's always the question of endogenous technological change. The key aspect there is incentives. As economists are always interested in incentives. When do the incentives arise to develop new ideas? Now, when you're thinking about new technologies, for example, I've worked on a project with the Washington State Tree Fruit Commission on mechanical harvesters. Why are they looking at that now as opposed to 10 years ago? Well, it's not a surprise. It was instigated by the increase in labor costs, reduced migration. So we try to bring it down to incentives. What are the incentives to develop those new ideas, and start from there? Sometimes it's easier to do than others, but that's kind of we try to provide a foundation for the whole thing, yeah. Everyone's hungry? All right, thanks.